Welcome to BioIT World's Trends from the Trenches podcast, your insider's look at the science, technology, and executive trends driving the life sciences. I'm Allison Proffitt, editor of BioIT World. This episode is hosted by Stan Gloss, founder of BioTeam, a life sciences IT consulting company at the intersection of science, data, and technology. Joining Stan today is Kiana Aran, Chief Scientific Officer at Cardea Bio. Aran pitches the promise of graphene. A single layer of carbon molecules, graphene is one of the most biocompatible tools for extracting valuable information without disrupting biological systems. Aran is creating graphene-based biological transistors for pathogen detection, CRISPR-based gene editing, and plant genotyping. All the while, she's equipping women to be leaders in the sciences. Let's listen in.
Good afternoon, Kiana. It's so nice to be connected with you today and really looking forward to our conversation. Back in the 1960s, there was a movie with Dustin Hoffman when he was the graduate, and everybody wanted to give him lots of advice in this movie. And the advice that they were giving him was one word: plastics. And that was just this. Today's conversation reminds me a little bit about that, because we're all hearing another word in the marketplace called graphene. And you being an expert in graphene and materials and the impact this could have in the life sciences market, I want to get into a little of that today, but maybe we can start by having you share a little bit about your background and how you came to becoming a graphene expert.
Yes. Thank you so much, Stan, for having me. It's a pleasure to be on your podcast. So a bit about my background. I'm originally from Iran, and I moved to the United States in early 2000s. And did my undergrad in electrical engineering. So my pure, expertise in electrical engineering, I wasn't feeling very connected with electrical engineering because it was sort of a very dry field for me, building transistors and antennas, and I wasn't connecting with that. So for my PhD, I decided to go to biomedical engineering and continued building devices and instruments, not necessarily electronic instrument, but bioelectromechanical instrument for diagnostic applications. And it wasn't until my postdoc at UC Berkeley where I really started being introduced to graphene material and graphene electronics and really utilizing them for making diagnostic systems. So this is how I got introduced to the field of graphene, and the first work I did with graphene was basically making glucose sensor using graphene material, where I had to build my own electronic devices to be able to sense glucose in blood, and this was a collaboration with Children's Hospital in Boston. So that's how I got introduced to graphene, and it just opened up a new era of research for me. And the more I did, the more I was fascinated by this material and the electronic properties that it was offering. And my field of research has really expanded from just diagnostic towards basically understanding biology even more with using this material, which I can dive into a bit more.
Well, that's a great introduction. Just curious, why graphene? What makes graphene special?
So maybe I start with my own why first, because then that leads to why graphene. So I think we live in a world of connectivity. We connect with our loved ones. We connect with our own, body to some extent using digital technologies. And that's from our phone, from our watches, from our, other digital instrumentation that we have. And this is somehow limited right now. For example, we know how many steps we take throughout the days. We know our heart rate. We know our oxygen saturation rate. We know if our loved ones are moving around, for example. But it's limited because in order to be connected with our health, we really need more information than just these signals and these health signals. And the major thing that it's required is the ability to be able to read the biosignals produced in our body in more frequently. That is limited today because we have to go to lab. The lab results are always printed on a paper. They're not followed up, in a form that you can really follow how your body is basically changing over time. And if there is any signal that could be detected, that could be indicative of some sort of pathologies. So as we move towards the world that digital will basically take over our healthcare, we have to think about, how do we use all of this modern system and modern electronic system that we have, which are accessible, which can actually be, scaled, in a way that, everyone can have access to it, to where we can utilize them for our, connecting with our own body, connecting with our health. This requires a material besides silicon, because silicon, which is the dominant material in our electronic industry today, has limitation. In order for us to be able to connect with our biology, we need to use a material that can connect with biology without impacting it. In another word, it should be a biocompatible material. That leads to why I chose, to work with graphene, because graphene is a single layer of carbon molecules. Everything in our body is made of carbon. So it's the most compatible material you can find that has amazing electronic properties, where you can build basically electronics from it that you can connect with biology, that you can conjugate with biology without impacting the biology and without biology impacting it. Because with silicon, the salt material in our biology will impact silicon performance, and silicon is not very easy to conjugate with biology because it's not a biocompatible material. So this is why I chose to work with graphene. And this is beside all other outstanding properties that this material has in terms of, the ability to rapidly detect electronic or charged signals. This is, again, a single layer of carbon molecules. So when you compare it with a bulk material such as silicon, you don't lose signal, because the signal can basically propagate throughout this carbon bond much faster, and we can read them faster, which makes it even better for biology, because biological events happen really, really fast. So if you want to really look at some of these biological events, you want to use, electronics that could, read these small signals without losing it, and also fast. So all of this made, graphene a super interesting material for me to work with, and this basically led to my involvement and my research on graphene electronic for healthcare applications.
So this is really interesting, because when you think about some of the instruments we're using, like a DNA sequencer these days, we're thinking about a technology that we're kind of translating light into signal, as opposed to we have to derive it from another source, whether it's a chemical reaction or a fluorescent reaction or something. We can't really go directly to the biology. So does graphene give us the ability to be direct?
So it's not only graphene, it's a combination of graphene with the right electronic that you use, right? So you use graphene in what sort of an electronic configuration? We use graphene in transistor configuration, which is really important, and that would lead me to the story of transistor later. But you're absolutely right. The light wavelength, it's big. So it basically misses the small biological molecules that exist in our body, such as like protein-protein interaction or DNA-protein interaction. And this is why we have to amplify it. We have to put optical labels to it to be able for us to actually detect it. With electronic, you don't have that. You actually are very flexible in choosing the wavelength of your electronic, and enable it to actually propagate through the smaller biological molecules, which will enable you to actually read this biological molecule, and not only read them, but based on their nature, you can modulate your electronic to just make it good enough to read those specific biology. For example, exosomes are bigger than proteins. You can actually play around with your wavelength, so you're more sensitive to exosome than protein. So these are the abilities that modern electronic will bring to us that we haven't really tapped into it to be able to basically connect with biology and be able to read this biological event. The combination of graphene with modern electronic, it's what makes this whole thing very powerful. And this is why we specifically work on field effect transistors made from graphene, because there is a lot of capabilities that this transistor will bring, that together with the property of graphene makes this electronic super interesting for these applications.
So that's very interesting that you kind of use the word transistor. I'm old enough to remember that people used to have transistor radios, and when I remember TVs had vacuum tubes in them. So how does this mirror the implementation of transistors from the past to transistors of the future?
Absolutely. So every gadget that you hold in your hands today, every electronic system that we have is made up of components that are made from transistors, from CPUs to GPUs to every single thing that you think about, integrated circuit. These are all made from transistors. As you mentioned, back in the days, we had vacuum tube, and these were basically playing as a role of switches. We had them in radios, we had them in telecommunication. In early 1900s, then AT&T commissioned Bell Lab to actually switch from vacuum tube type of switches to switches that are smaller, that consume less energy, because if they wanted to have long distance communication, they couldn't just work with vacuum tube because they were constantly burning. They had to constantly go change them. So they really needed a lot of maintenance. So it was around early 1950s when William Shockley and his colleagues, by changing the material from, basically working with vacuum tube to silicon and germanium, they were able to create switches that were faster, that, they consumed less energy. At the time, they just wanted to overcome the problem of telecommunication. What they didn't know is that the invention of transistor really enabled the whole, field of applications and capabilities. We moved to smaller computers, calculators, smaller computing systems because of this invention. Transistor got invented, and basically, which was the result of changing to a silicon material, which enabled them to do that. And then from that, in 1960s, 1970s, we started having cheaper transistors. We started making integrated circuit, and those integrated circuit led to, a small laptop that I have right now in front of me, and I can, communicate with you through it. But we have reached an era where really silicon has become a limitation now. So if you're thinking about, with all of this wonderful gadget, electronic and this modern electronic that we have, how can we utilize them for healthcare application towards moving to a future where, we can have digitalization in our healthcare? Silicon is not the right material. Now we have to basically expand to next generation of material that enable us to connect with biology and create transistors that are made from something that is not silicon anymore, something, mostly 2D material, quantum material. And because of the reason I mentioned to you and the compatibility and carbon-based properties of graphene, it's a very, interesting material as the replacement for silicon, specifically for healthcare applications.
So that was a great explanation of how what's something that started off old is new again. And this metaphor of thinking about this as a transistor. So how are you using this in real life? Do you have any examples of some of the work that you've been doing to kind of get at these biological signals that are difficult to kind of get at?
Absolutely. So I'm going to give you two examples. One will show you how this material can basically replace the existing test and can make it easier and more accessible. And I'm going to give you another example of how these graphene transistors can enable you to do things that is impossible to do otherwise, and basically tap into biology to develop the next generation of technologies. So this transistor that we use today, and this is a transistor made from graphene. It has actually 15 transistors inside. you can basically use pathogen detection. For example, in terms of COVID, let's say, when you're taking a pathogen test, those lateral flow assay tests that you have in your house, these are basically antibody-antigen reaction. You have an antibody that binds to the SARS-CoV-2 spike protein, and then you would see an optical signal. It's not quantitative. It can just give you a yes or no answer. Then if you want to do a molecular test, you have to go to the lab. They take your they take the sample, and they detect the RNA molecule. They amplify the RNA molecule, and then they detect it to see if the SARS-CoV-2 RNA is present or not. You can do both on a single system right now with these transistors, because these transistors, they don't need optics. They don't need optical labels, and they only monitor the interaction of a capture molecule, a biology that we actually conjugate with this transistor that can react to a SARS-CoV-2 RNA or the SARS-CoV-2 spike protein. So you can envision a single platform that can monitor these signals simultaneously. So, when these are scaled and manufactured, in your homes, you're not only giving a pathogen test, you can give a pathogen test. You can also give a molecular test, basically looking at the RNA of the virus. You can also quantify that, meaning that how much of that you have. Are you infectious? Can you go out, or you are at the level which you have to stay still home until you're completely clear. So these are the capabilities that these transistors can offer, which can replace existing platform that we have right now. The other thing is that the power of this system, they can connect with biology without impacting it. And it opens up a new generation of technologies that use biology as an element. I'll give you another example. CRISPR is a technology that was developed by bacteria, over billions of years, right? And it's a technology that defends bacteria against viral system. It's basically a two-component system. It has an enzyme and an RNA molecule bound to that enzyme. The RNA molecule guides the enzyme to go to a specific place in the DNA sequence. And if it finds it matches match sequence, it basically cleaves and destroys it. So it's a very precisely designed search engine designed by nature to identify the sequences of bacteria. In 2012, we were able to actually identify how we can utilize this technology to edit our genome, to basically improve and treat genetic diseases by identifying the diseased region of the DNA, basically cut it and then replace it with the right DNA sequence. So it has opened a new era in research. But if you look at this, CRISPR system as a technology, it's a search engine. Can we actually monitor the function of this enzyme in a way that we can utilize them for diagnostics? Because if it's a search engine, can we actually monitor its function and see if it can find the sequence of our interest for genotyping application? So what we have shown is that if we put a CRISPR molecule on these transistors and we programmed it to detect, specific genetic diseases or genetic mutation in the whole DNA, then we are bypassing a whole bunch of the steps in sample prep in existing method, where you have to take a DNA sequence, chop it, amplify it, label it, basically, go over it by a bus before you can detect it. This will enable you to use biology as technology and, generate systems that can really utilize the power of biology for application that we already have a need for. So we have used this CRISPR. We designed a system basically to do genotyping for diseases, and we have shown that we can detect genetic diseases in diseases such as sickle cell disease, ALS, Duchenne muscular dystrophy, without the need for all of those amplification steps. And by just using biology as a technology element with these transistors, which are sensitive enough, which are friendly enough with biology, that allow biology to do their function. We have also, in my company, we also have worked with the industry collaborator where we're looking at genotyping in plants, where these are farmers that they want to make sure that they have the right plants, or industries that want to make sure that they buy the right plants, and they want to do genotyping on site. There is no capability or the infrastructure that is required to do amplification there. You cannot do amplification and have those labs set up in the field. So this will enable you to have tricoders, basically, where you can do molecular testing and identify if you're actually having the right, or you're buying the right, basically, plant material to for distribution, for example. So these are some of the applications that these graphene-based transistors can bring, which no technology can do that.
Yeah. So you were holding up, well, since we're a podcast, you're holding up the transistor. I can see them, but our audience can't. So Kiana is actually the chief scientific officer at a company called Cardea Bio. So if you want to take a look at the pictures of the transistors, you can see them on that website. You said a couple of things that caught my interest. You mentioned the word amplification a number of times, associated with the current method of technology, measuring something in small signal, and then having the need to amplify it to see it. What I think I heard you saying is that with the graphene-based system, you're not needing the steps of amplification, and is that a pretty big benefit of the system?
Absolutely. So when you think about the majority of the diagnostic or sensing systems that we have, we amplify the signal. For example, we amplify the RNA molecule that we are trying to detect. We amplify the DNA molecule that we're trying to detect. So basically, we copy many of it, so we make it detectable. That is itself prone to a lot of mistake and a lot of false positive or false negative. And it also requires it requires an infrastructure to do that, because you have to design primers, you have to have a clean environment to make sure you're not introducing or amplifying some sort of a contaminant. And with our system, we don't amplify the signal. And this is what makes us be able to quantify too, because if you're amplifying a signal, you're generating a million copy of it. You can't really quantify it because you have already amplified it, right? Because we don't amplify the actual analyte, the actual RNA, the actual DNA, the actual protein, this will enable us to bypass a lot of steps, sample prep step. In addition, it allows us to be quantifiable because we're detecting the actual signal, not the amplified version of it.
That's terrific. And again, we're moving toward, many companies that I talk to are working towards decoding biology, because biology is a very complex system. So the more and more we can get insights into signals that we never saw before, the more and more we can gain understanding of the biology that we're looking at. Is that true?
Absolutely. So my academic lab is actually working on the next generation of this transistor that really are designed to tap into biology first, to understand the enzyme function and what are the factors that are impacting an enzyme function. This could be a CRISPR molecule. This could be other enzyme of interest that are not interesting for basic science perspective, but if they are interesting for us, for our industry, as if we were to utilize this enzyme for some applications, for treating diseases or for diagnostic or for synthesis application, how can we actually improve the function of this enzyme and the modification that we're creating in our protein synthesizing world, how those things will actually impact the function of those enzymes, because again, we're not hindering the activity of the enzyme, and we're able to monitor these activities in real time. So that's a whole new area of research that my lab is basically working on.
That's fantastic. Now, in the rest of the time that we have, I want to pivot over to something else. You recently won an industry award for your work. And with that award, you actually set up a foundation. And I think I'd love to hear a little about that story and what your foundation is doing, because I think I know what it's doing, but my audience doesn't. So I think it would be very interesting to share a little of that if you have the rest of our time.
Absolutely. So last year I won the Nature Journal Research Award for inspiring women in science, and that award came with a money that I decided to use to promote other women in STEM. One of the things that I have learned throughout my career and my own personal experiences, because as I mentioned, I migrated from Iran, where we had a lot of limitations in many aspects of our lives. And I was so passionate to do science. I was very passionate about science that every little opportunity was a window for me that I would jump on to take advantage of and basically use it for science and research. And opportunities would never pass by us without us basically at least trying to take advantage of them. But I realized when I moved to US, and there was so many opportunities here. Of course, there are limitations, especially for women. But if we were to focus only on limitation, we can't move forward, So as we are trying to get more women in the STEM, as we are trying to really encourage women to actually participate more in the STEM field, we also have to think about the areas that women are not playing a major role. That's leadership, that's executive roles in industry. And what we thought that is really lacking in our community is an organization that can promote skill set that we need as an highly trained women in science, that we could become, how could we become leaders where we can transfer our knowledge to industry, because again, our research should be a product or should be a foundation for future products. I think scientists can play a major role in pushing the industry forward if we learn some of the leadership skills that we don't learn in academia. And as women, if we focus more on the opportunities ahead of us rather than focusing on limitation. So when you enter a room that you feel you don't belong because you're a woman, change your perspective. Maybe you are in a room and you feel you don't belong because you don't have that skill set. Let's go and learn those skills, identify the skills that we need. Let's go learn them and, just focus on, there's an opportunity. There's an opportunity in you identifying a lack of a skill set that you can go after. So I have identified a few of those shortcomings in my skill set that I try to take advantage of, using the community that I had in my startup, the great, co-founders and colleagues that I had who were extremely helpful in promoting women. And I want to, be able to somehow have other, women to basically get access to those skill sets and basically shift their focus on the positive aspect so they can also bring their outstanding research to fruition, to a product, and to something that could benefit the human life. So over the past few months, we were trying to basically identify the first cohort that will join the nebula. We call it the nebula because that's where stars are born. And I think every scientist is a star because we put our whole life towards, promoting science, and we should be given, opportunities to basically be involved in pushing that science towards something that could benefit human lives. So now in the process of basically identifying the first cohort, it's not a big cohort, it's a small. We want to start small to make sure that it basically reaches the goals that we have, and then we will expand it to more women in science to basically be able to utilize those opportunities. We offer leadership classes in collaboration with other organizations, and I'm not trying to create everything because there's a lot of outstanding organizations that have brought, some aspect of what we need to promote women in STEM and to promote them for leadership roles. So we're trying to partner with them, and we have partnered with a few, help women build their social capital, because that's something that I think we women don't pay a lot of attention to. We are designed to basically have an agenda and just check mark everything in our agenda. And we normally don't put a lot of time on building our social capital, which I think is very, very important, and basically giving them those skills that is important for them to be able to become great leaders that they are already. It's just that, helping them get there.
So if my colleagues want to find out more about your foundation, where would they find information?
So we have the website. It's arannebula.com. It's my last name, nebula.com. And we would love if people want to, support our mission and help us if they have something that they think would be really beneficial for our organization. We would love them to, help us and become a part of it. As for the cohort, we are very selective at this moment on who can actually join the cohort because we are, again, focusing on women that could become role model for next generation of women. So it's very important for us that we select the people who have the interest to become the leaders. So that's been a bit of a challenge, who are the best first cohort. But with training that we offer them, and I think we will be able to expand the program significantly next year.
Well, thank you so much for sharing the story of graphene and the Aran Nebula. And I love the idea. This is where stars are born. And anyway, so thank you very much for joining us today. And I will actually put some of this information in our show notes so that the links to Cardea Bio and the Aran Nebula and maybe a few articles from Kiana. Thank you so much, Kiana, for being my guest today.
Thank you very much for having me.
Thank you for listening to BioIT World's Trends from the Trenches podcast.